So today I'm going to tell you about the first glimpse of the very first galaxies that JWST is showing us and all the surprises we're finding at these unprecedented redshifts. And we really needed JWST to see it. And so it really lights up at 2 micron all the way out to 4 micron, but then it's completely invisible. This very smoking gun signature of very distant galaxies.
In the vast expanse of the cosmos, the mystery surrounding the origins of our universe has captivated the minds of scientists and astronomers for centuries. At the heart of this cosmic mystery lies the Big Bang theory, a captivating narrative attempting to unravel the cosmos's inception. The James Webb Telescope, in an ambitious quest to delve into the cosmic archives and shed light on the elusive moments before the Big Bang, stumbled upon a huge structure older than the universe. This revelation sent reverberations through the scientific community, not merely challenging prevailing theories, but introducing an unexpected and chilling narrative twist that defied all anticipations. Join us as we explore how James Webb just detected a huge structure older than the universe. Astronomers' chance discovery with James Webb. The genesis of this revelation traces back to an astronomer who brought to light a finding observed through the James Webb Telescope. Astronomer Rowan Naidu, while at home with his girlfriend, stumbled upon a galaxy during his examination of images sent by the James Webb Telescope. The celestial body, recognized by Naidu as mysteriously colossal, traces its origins back to the Big Bang era, surpassing the age of any galaxy previously known to science. This revelation was particularly astonishing to Naidu, who promptly shared the discovery with his girlfriend, inviting her to witness the celestial spectacle. Naidu's team commended him for this groundbreaking discovery, prompting them to diligently delve into further analysis. A few days later, the team published a comprehensive paper on the newly discovered galaxy, aptly named Glass Z13. This unexpected revelation captivated the global scientific community, halting its collective breath in disbelief that such a discovery could emanate from the James Webb Telescope mere weeks after its launch. The James Webb Space Telescope, currently the most potent tool in the hands of scientists and astronomers, serves as the successor to the Hubble Space Telescope. Orbiting the Sun at a distance of 1.5 million kilometers, shielded from earthly interference, it boasts a sunshade equivalent to the size of a tennis court. Outfitted with segmented mirrors and highly sensitive instruments, the telescope aims to unravel unexplored details about our universe. This state-of-the-art telescope has entered a scarcely probed era, investigating the formation of the very first stars and galaxies. While this period remains obscured by exotic physics, the recent discovery of a galaxy from the Big Bang era has opened new avenues for cosmologists. The James Webb Telescope's ability to explore such phenomena in the early universe presents an opportunity to either confirm prevailing consensus models or unveil gaps in understanding, potentially leading to groundbreaking discoveries. This includes scrutinizing uncertain influences of dark matter and dark energy, as well as comprehending the intricate interplay between starlight, gas, and dust. Initial projections had anticipated challenges in locating small galaxies, but the telescope's rapid success in uncovering ancient celestial bodies defies those expectations, promising an exciting era of scientific exploration and revelation. The powerful $10 billion telescope surprised scientists by contradicting their predictions. Once it beamed back its initial images of the distant universe, astronomers and cosmologists had to revisit their assumptions. Among the first to analyze the images was astronomer Naidu, who discovered galaxies that surpassed expectations in terms of size, age, and brightness. This unexpected finding, shared by multiple research groups analyzing the telescope's images, sparked a kind of competition among scientists, as each group reported record-breaking galaxies. This unforeseen discovery led scientists to question whether these anomalies were real or if there were flaws in the telescope's initial observations. They pondered whether these anomalies could challenge our current understanding of the universe, suggesting it might be more strange and complex than previously thought. The significance of these discoveries by the telescope extends to the very foundations of our understanding of the universe's emergence from ancient chaos. The telescope's early findings could potentially reshape our understanding of cosmic history, including not only distant epochs and galaxies, but also our existence in the Milky Way. Mark Makorian, a senior advisor for science and exploration at the European Space Agency, remarked that the purpose of such machines is not just to confirm existing paradigms, but to challenge and break them. He emphasized that the James Webb Space Telescope has been in the making for billions of years, tracing back to the Space Telescope Science Institute's work in 1985. The JWST's origins can be traced back to a question posed by Riccardo Giacconi, the director of the STSCI at the time, to Garth Illingworth, his deputy, about what would come after the Hubble Space Telescope's discoveries. Despite initial resistance, Illingworth and his team started conceptualizing the Next Generation Space Telescope, NGST, later renamed the James Webb Telescope. The need for the JWST became urgent in 1995 when astronomers, using the Hubble, discovered thousands of galaxies in a seemingly empty patch of sky, challenging scientists' expectations of the early universe. From Hubble to Webb. Despite the incredible discoveries made with the Hubble Deep Field, astronomers and scientists wanted more. This desire led to the creation of the James Webb Telescope, a project that spanned over 2 decades. Launched on December 26, 2021, the telescope reached its deep space destination a month later. Once there, the James Webb Telescope underwent rigorous testing until July 2022 to ensure it would perform optimally. It then began its first year of scientific observations, known as Cycle 1. These early observations included high-impact programs covering various disciplines. 2 notable programs were the Cosmic Evolution Early Release Science Survey and GLASS. These programs focused on studying galaxies in the early universe by examining small sections of the sky. Initially, scientists didn't expect much from the James Webb Telescope, maybe a clearer version of the Hubble Deep Field. However, the telescope surpassed expectations. The first observations revealed galaxies, confirming the findings of astronomers like Naidu. This influx of scientific papers detailing the telescope's initial observations wasn't accidental. As data streamed down, astronomers and theorists eagerly wrote papers and developed theories based on their discoveries. Some scientists, though, expressed concerns about the rush to publish numerous scientific papers about the initial observations. Collaboration issues with the James Webb Telescope could have influenced results. Despite this, the sheer number of observed galaxies and consistent reports make it unlikely that all scientific findings are incorrect. To address uncertainties, scientists plan follow-up observations with the James Webb Telescope. Many research groups are submitting proposals to use the telescope for further observations. These proposals primarily aim to scrutinize high-redshift galaxy candidates. Among the upcoming programs is the Cosmos Webb Project, which intends to significantly increase our knowledge of early galaxies. By observing a wide sector of the sky for extended periods, scientists hope to detect thousands of galaxies yet unknown. This ongoing mission showcases the continuous efforts to explore and understand the vast mysteries of our universe. Electric universe model and galactic power sources. Various theories attempt to explain the origin of the universe. One such theory is the steady-state universe, which suggests that the universe is continuously expanding but maintains a constant overall density. In simpler terms, it's like an ever-growing but unchanging cosmic structure. In this model, as new elements constantly form, older astronomical objects become difficult to observe. Another competing theory is bouncing cosmology, or the Big Bounce model. According to this idea, the universe undergoes a cycle where it shrinks to a minimal volume and then bounces back into a subsequent expansion. This suggests a pattern of contraction and expansion, challenging the notion of a one-time beginning. Then there's the plasma or electric universe model, which introduces the concept of plasma as a fundamental player in cosmological events. Plasma is a high-energy state of matter, and in this theory, it plays a crucial role in shaping the universe. The model proposes the existence of electric currents flowing along plasma filaments, influencing the structure and energy of galaxies. These currents even reach stars, acting like cosmic power sources, akin to fluorescent bulbs and contributing to the formation of planets. The prevailing theory regarding the origin of the universe is the Big Bang, a concept popularized and further disseminated by the television show The Big Bang Theory. This theory has gained widespread acceptance within the scientific community, evolving from initial observations that galaxies are rapidly moving away from each other in all directions, suggesting a primordial explosive force. The origin of the Big Bang Theory can be traced back to the 1920s, when Belgian priest Georges Lemaitre proposed that the universe originated from a single primordial atom. Edwin Hubble's subsequent observations, revealing galaxies moving away from us, and the 1960s discovery of cosmic microwave radiation provided substantial support for the theory. Over the years, scientific inquiry has helped refine our understanding of the Big Bang's chronology. In the first 10 to the power of -43 seconds of its existence, the universe was incredibly compact, less than a million billion billionths the size of a single atom. At this point, the fundamental forces of gravity, electromagnetism, and the strong and weak nuclear forces had not yet separated into distinct entities. Although current theories haven't fully explained how a single unified force operated, the universe expanded, allowing the fundamental particles to form as they cooled. By the time the universe was a billionth of a second old, it had cooled sufficiently for the fundamental forces to separate, and the universe's fundamental particles began to take shape. The extreme heat of this early state prevented the assembly of many subatomic particles, such as protons. As the universe continued expanding, the quark-gluon plasma, a hot primordial soup, gradually cooled. Particle colliders like CERN's Large Hadron Collider can recreate this plasma. During the universe's early days, intense radiation allowed colliding photons to form pairs of particles made of matter and antimatter. While the early universe likely contained equal amounts of matter and antimatter, as it cooled, photons no longer had the energy to create these pairs. Consequently, particles of matter and antimatter paired off and annihilated one another, leaving behind the excess matter that constitutes celestial bodies and galaxies. The presence of matter and our existence are indicative of a subtle rule imbalance known as CP violation, wherein matter prevailed in the early universe. Physicists continue to explore the mechanisms behind this victory of matter over antimatter. Infinite density and quantum ballet. Before delving into what transpired before the Big Bang, it's essential to address two intriguing questions related to the Big Bang itself. Firstly, the Big Bang did not occur at a specific location. Unlike a dynamite explosion with a center and outward shrapnel, the Big Bang saw space itself pop into existence and expand everywhere simultaneously. Analogies, such as a rising cake with receding raisins representing galaxies, help convey the idea of expansion without a center. Secondly, the Big Bang wasn't a one-off event. The inflationary vacuum preceding it experienced exponential growth, doubling its volume and energy. This inflationary vacuum, a quantum phenomenon, eventually led to the unfolding of the universe as we know it. Now, turning to the period before the Big Bang, scientists are particularly intrigued by the concept of singularity, also known as the Planck epoch. This earliest known period of the universe involved all matter condensed into a single point of infinite density and extreme heat. During this epoch, the quantum effects of gravity dominated, and other physical forces were not of equal strength to gravitation. The Planck epoch endured from 0 to approximately 10 to the power of -43 seconds, a duration measured in Planck time. The extreme heat made the universe highly unstable, prompting its expansion and cooling. The subsequent phase, from approximately 10 to the power of -43 to 10 to the power of -36 seconds after the Big Bang, marked the universe crossing transition temperatures. Forces governing the universe began separating, starting with gravitation detaching from gauge forces, which account for strong and weak nuclear forces, and electromagnetism. In the following phase, from 10 to the power of -36 to 10 to the power of -32 seconds after the Big Bang, the temperature dropped, allowing electromagnetism and weak nuclear forces to separate. forming two distinct forces. The inflationary epoch, extending from 10 to the power of negative 32 seconds in Planck time to an unknown point, involved the universe's homogeneous filling with high energy density. This led to rapid expansion, cooling, and the occurrence of baryogenesis, where particle-antiparticle pairs were continuously created and destroyed, favoring the predominance of matter over antimatter in the present universe. After inflation ceased, the universe consisted of a quark-gluon plasma and other elementary particles. From this point onward, the universe began to cool, and matter coalesced, forming the structures we observe today. The James Webb Space Telescope is anticipated to provide valuable insights by allowing scientists to peer billions of years into the past, offering a glimpse behind the veil of the Big Bang. Following the cooling epoch, a period marked by a decrease in the universe's density and temperature, the energy of each particle began to decline. Phase transitions continued until the fundamental forces of physics and elementary particles assumed their present form. As particle energies dropped to levels measurable by particle physics experiments, speculation about this period decreased. Subsequently, the structure epoch unfolded over billions of years, culminating in our present day. During the structure epoch, slightly denser regions of the initially uniform matter in the universe were gravitationally attracted to each other. These regions grew denser, giving rise to gas clouds, stars, galaxies, and other astronomical structures observed today. This transformative phase saw the emergence of the modern universe with visible matter, distributed across structures of varying sizes, from stars and planets to galaxies, galaxy clusters, and superclusters. These structures are separated by vast expanses containing few galaxies. The question of where the Big Bang took place is indeed fair, considering that pinpointing an explosion's location is feasible in everyday experiences. However, the reality is different when it comes to the Big Bang. There is no specific spot, no ground zero, because the Big Bang occurred everywhere. Despite the term invoking notions of explosions or detonations, it's crucial to understand that the Big Bang was not a localized event. Rather, it unfolded universally. Inflation's quantum fluctuations and cosmic homogeneity. The horizon problem is one of the unresolved issues associated with the widely accepted Big Bang theory. This issue arises from the fact that different regions of the universe, although visible to us, may be invisible to each other due to vast distances. Despite these regions having the same temperatures and other physical properties, the cosmic microwave background, CMB, is observed to be homogeneous everywhere. This poses a challenge because, according to our understanding, information should not travel faster than light. The observed isotropy of the CMB, or its uniformity, raises questions about how different regions of the universe with no direct contact could exhibit the same properties. The resolution to this apparent inconsistency is proposed by the inflationary theory. In the inflationary model, a homogeneous and isotropic scalar energy field dominates the universe during a very early period. Heisenberg's uncertainty principle plays a role in this theory, suggesting the presence of quantum thermal fluctuations during the inflationary phase. These fluctuations, when magnified to a cosmic scale, serve as the seeds for the formation of all current structures in the universe. Inflation predicts that these primordial fluctuations are nearly scale invariant and Gaussian. The accuracy of these predictions is crucially supported by measurements of the cosmic microwave background, reinforcing the credibility of the inflationary theory. Despite the horizon problem being a challenge, the inflationary model provides a compelling explanation for the observed uniformity in the CMB, offering a plausible solution to this long-standing puzzle in cosmology. The scenario before inflation began is described as the universe being incredibly small, with a diameter of about 10 to the power of negative 24 centimeters. During this pre-inflationary period, all matter and energy were in close and uniform contact. In an instant, the universe expanded exponentially by a factor of about 10 to the power of 50, propelling matter and energy to the farthest reaches of the universe. Importantly, the information from the pre-inflationary universe didn't need to travel at the speed of light, but rather at the speed of inflation. offering a solution to certain challenges in the Big Bang theory. One such challenge is the flatness problem. According to Einstein's field equations of general relativity, the presence of matter and energy on smaller scales affects the structure of space-time, making space appear flat locally. This is analogous to how the Earth's surface appears flat when observing a smaller area. However, on a larger scale, space becomes curved due to the gravitational effect of matter, and the curvature depends on the density of matter. Concerning events preceding the Big Bang, human curiosity strives to understand what occurred before the universe's origin. However, this is a complex endeavor. The cosmic dark ages present a barrier, preventing direct observation of what transpired during the Big Bang. These dark ages were a time when the universe was shrouded in a fog of neutral hydrogen, trapping the light of the first stars and galaxies. The fog persisted until about 1 billion years after the Big Bang, when neutral hydrogen was reionized, allowing light to escape once again. Even before the Dark Ages, the lack of observable light is attributed to the fact that, aside from hydrogen atoms, the majority of the universe was composed of dark matter. Dark matter does not emit light, contributing to the scarcity of observable light before the formation of the first stars. The cosmic dark ages, combined with the elusive nature of events preceding the Big Bang, pose challenges to our understanding of the early universe. Now it's time for today's subscriber pick. James Webb just detected a huge structure older than the universe, and this is causing astronomers, including Alison Kirkpatrick at the University of Kansas, to question the long-held Big Bang theory. Contrary to expectations, JWST images depict galaxies that are unexpectedly small, smooth, old, and numerous, challenging predictions of the theory. Some scientists, like Eric Lerner and Ricardo Scarpa, argue that the redshift of newer galaxies in the images is 2 to 3 times greater than anticipated, conflicting with the idea of an expanding universe. The JWST findings also defy expectations of mangled galaxies, resulting from collisions and mergers, instead revealing overwhelmingly smooth spiral forms, challenging the common belief in galaxy mergers. Furthermore, the age of some galaxies in the images, exceeding 1 billion years, contradicts the Big Bang's assertion that nothing predates the event. Additionally, a yet-to-be-published paper indicates that large galaxies existed shortly after the hypothesized Big Bang, challenging the theory's prediction of a cosmic dark age. Overall, the JWST data prompts a reevaluation of established cosmological theories and raises questions about our understanding of the early universe. Let us know what you think about this discovery, Hawking's shuttlecock and the time-space paradox. To explore what happened before the Big Bang and address the question of where the initial energy came from, Stephen Hawking proposed a concept known as the no-boundary proposal. In collaboration with James Hartle, this proposal was fully formulated in a 1983 paper. The no-boundary proposal envisions the shape of the cosmos resembling a shuttlecock, akin to how a shuttlecock has a diameter of 0 at its bottommost point and gradually widens on the way up. According to this proposal, the universe smoothly expanded from a point of 0 size, derived from a formula by Hawking that describes the entire shuttlecock structure. This structure, often referred to as the wave function of the universe, encompasses the entirety of the past, present, and future simultaneously. Hawking's proposal eliminates the need for contemplation about the seeds of creation, the existence of a creator, or any transition from a time before. The no-boundary proposal offers a radical reconceptualization of time. While we perceive the universe as expanding and evolving from one moment to the next, the proposal suggests that each moment is a cross-section of the shuttlecock. Time, in this view, consists of correlations between the universe's size in each cross-section and other properties, particularly its entropy or disorder. As the shuttlecock widens, entropy increases, creating an emergent arrow of time. At the rounded-off bottom of the shuttlecock, where correlations become less reliable, time ceases to exist and is replaced by pure space. In this framework, Hawking and Hartle considered the possibility that the universe began as pure space rather than dynamical space-time. This unique perspective led them to the shuttlecock geometry, and they defined the no-boundary wave function to describe such a universe using an approach pioneered by Hawking and physicist Richard Feynman. The no-boundary proposal challenges traditional notions of the universe's origin and provides an intriguing avenue for contemplating the nature of time and space. The theory of infinite bangs and contractions. In the 1940s, physicist Richard Feynman introduced a groundbreaking method for calculating quantum mechanical events, particularly predicting outcomes of particle collisions. This method, known as the path integral, involves summing up all possible paths particles could take during a collision, favoring straightforward paths over convoluted ones. The result, called the wave function, offers a probability distribution indicating possible states of particles post-collision. In later years, Stephen Hawking and collaborators explored the wave function further using holography. This innovative approach treats space-time as a hologram, envisioning a universe shaped like a shuttlecock, with the geometry of the past projecting off the present. Neil Turok and colleagues at the Perimeter Institute developed a cosmological model inspired by the no-boundary proposal, featuring two shuttlecock-shaped lobes resembling an hourglass with time flowing in both directions. This model realizes CPT symmetry, reflecting matter and antimatter, left and right, and forward and backwards in time. However, it introduces a singularity, a pinch in space-time requiring an understanding of the unknown quantum theory of gravity. Hawking's exploration of the pre-Big Bang period, describing the quantum cosmos or the wave function of the universe, fascinates physicists. Quantum cosmology emerged as researchers explored alternative ideas about the universe's origin, testing predictions and contemplating philosophical implications. The no-boundary wave function, a simple explanation proposed by Hawking, sparked interest. Alternative theories challenge the idea that the Big Bang marked the universe's beginning. One proposes a mirror universe where time runs oppositely and other properties reverse. Another suggests the Big Bang wasn't the absolute beginning, but a transition point in a cycle of expansion and contraction, implying potentially infinite Big Bangs. Despite challenging aspects of the prevailing Big Bang theory, it remains the leading explanation for the universe's origin. Recent images from the JWST prompt scientists to reevaluate the Big Bang theory's credibility. The simplicity of the model, stating the universe began from an infinitely hot, dense point, expanding over billions of years, is questioned. The JWST's observations may lead to further exploration and refinement of our understanding of the universe's beginnings. JWST challenges conventional wisdom in cosmology. The Big Bang theory, which has long been upheld as an unquestionable truth by most cosmological theorists, is facing scrutiny and concern from some, including astronomer Alison Kirkpatrick at the University of Kansas in Lawrence. The latest data from the JWST has led Kirkpatrick and others to question the foundations of their work in the field. The observed characteristics of galaxies in the JWST images seem to challenge the predictions of the Big Bang hypothesis. The galaxies appear unexpectedly small, smooth, old, and surprisingly numerous, creating an apparent incompatibility with the expectations set by the Big Bang theory. According to a few scientists, the theory proposes that in an expanding universe, objects such as galaxies should exhibit a particular optical illusion, where they appear smaller with increasing distance. However, the JWST images show galaxies becoming smaller beyond a certain point, even those with greater luminosity and mass than our Milky Way, which contradicts the anticipated behavior based on the theory. In the view of scientists like Eric Lerner and Ricardo Scarpa, the redshift of newer galaxies in the JWST images is 2 to 3 times greater than expected, challenging the idea of an expanding universe. Lerner and Scarpa had previously published results based on Hubble Space Telescope images, suggesting that galaxies exhibit a redshift that aligns with the expectations of a non-expanding ordinary space. They anticipated that the James Webb Space Telescope would confirm their hypothesis, Contrary to the expectations of Big Bang theorists, who anticipated observing badly mangled galaxies resulting from multiple collisions and mergers, the JWST images present galaxies that do not align with these predictions. The discrepancy in the observed data is leading some astronomers to reevaluate their understanding of the universe's dynamics and question the previously unquestioned validity of the Big Bang theory. However, the JWST images revealed overwhelmingly smooth disks in neat spiral forms similar to galaxies observed in the present day. Contrary to expectations, the data from the JWST challenge the idea that galaxy mergers are a very common process. According to Lerner and Scarpa, the data utterly destroys the merger theory. The Big Bang theory suggests that the most distant galaxies in the JWST images are observed as they were about 400 to 500 million years after the origin of our universe. However, some galaxies in the images exhibit stellar populations that are at least 1 billion years old. This challenges the Big Bang theory, which posits that nothing could have originated before the event. The authors of the Panic article argue that the existence of these galaxies is evidence that the Big Bang did not occur. The expectation, based on the Big Bang theory, was that as the JWST looked further into space and time, galaxies would become fewer, eventually leading to a cosmic dark age with no galaxies. However, a yet-to-be-published paper indicates that galaxies as large as the Milky Way were common just a few 100 million years after the hypothesized Big Bang. From the Big Bang standpoint, distant galaxies are supposed to be intrinsically smaller, but one notable galaxy, JZ2, mentioned in the paper, is far more luminous than the Milky Way, and yet is calculated to be just 300 light-years in radius, 150 times smaller than the Milky Way. The JWST images, along with this new research, are challenging established theories and prompting a re-evaluation of our understanding of the universe's early history. Debunking misconceptions about the Big Bang theory and JWST discoveries. David Lerner's critique of the Big Bang theory, citing 16 wrong predictions and only one correct prediction, helium abundance, raises questions about the model's accuracy. Lerner contends that predictions regarding lithium abundance and the presence of large-scale structures pose challenges to the theory. However, most cosmologists and astronomers argue that there are explanations for these doubts, emphasizing that the Big Bang theory is not invalidated. In response to Lerner's concerns, astronomers point out that the observations made by the JWST haven't disproven the Big Bang theory. While the JWST has unveiled unexpected and peculiar aspects of the universe, the fundamental principles of the Big Bang remain intact. The theory relies on 3 key pillars of data: the higher redshift of more distant galaxies, the cosmic background of microwave radiation, and the relative abundance of elements in the early universe. The Standard Model of Cosmology, also known as the LCDM model, has been developed over the years to encompass various phenomena, such as the acceleration of cosmic expansion and the clustering of galaxies. The Tolman test, for example, predicts that if the universe were non-expanding and static, the surface brightness of galaxies would be consistent regardless of distance. The JWST's images, revealing dimmer surface brightness in distant galaxies, support the idea that the universe is expanding. A common misconception addressed is that redshift proves galaxies are moving away due to speed. In reality, the expansion of space itself is responsible for the redshift, emphasizing that galaxies are not speeding through space, but are carried apart by the expanding universe. Although the JWST's findings may not entirely align with predictions, astronomers anticipated puzzling data and invested in the telescope precisely for this purpose. The collected data doesn't undermine the Big Bang model. Instead, it challenges some assumptions. Scientists acknowledge that the JWST's contributions provide valuable insights and potential refinements to our understanding of the early universe. The discrepancy between predictions and observations underscores the ongoing nature of scientific inquiry and the need for continued exploration and refinement of cosmological models. Thanks for watching, and we'll see you in the next one.